Hello and welcome. Welcome to our Towards Net Zero Renos webinar series. We are at webinar 5 of 5 for our delivery of these topics. We are at the window selection and detailing, getting it right and airtight from design to install. I want to welcome you all here for these Renovating for High Performance series. We've had a great success over the past 4 series. This is the 5th one. And so I just want to introduce the team here, as well as what we're going to be getting into today. As we get through this seminar, this session, the Q&A, please put all your questions in the Q&A. Please use the chat for more conversational. If you put a question in the chat, it will likely get missed. So please make sure that all your questions go into the Q&A. There will be a survey monkey just before we break out into the question and answer section, where you get to ask all of the presenters questions and more details about the information that they presented. And all of the presentations will be sent out following this webinar. All right, so we're getting into windows. So windows are the eyes of the houses, but they also come with complications. We know, and you'll see, we'll be asking about how often it is that you come across where when you're removing a window, what is the damage that is represented there, which means we need to do it better going back in. So as renovators, we need to understand all of the nuances, but when we're looking at high performance renovations, we have such a greater impact on, now we're doing that integrated design with what is the impact of the windows on the heating and cooling, what are the impacts on the envelope, and so we're going to get into that to optimize your projects. And when we talk about optimizing projects, we also look at optimizing our teams. So I do want to give a shout out to another initiative that CHBA has, where we are offering training rebates for all of our building science, net zero builder, renovator, as well as the building officials. Make sure your building officials know the work that you're doing so that you can bring that team together right from the get-go. So these are initiatives, these are rebates that are offered through our CAF initiative. So make sure you take advantage of those for your teams. So the team behind developing this webinar series, we've been talking about this for 2 years with Building Knowledge Canada, who are our lead consultants. We have a lot of people working on these, but these are the team behind. We have Lori Howe and Brendan Fraser on my team at CHBA National working on this, and Andy Oding, Toby Smith, and Kimberly Cobb have been in the background working on all of this and bringing all of these sessions forward. So this is the last, as I mentioned, of our 5-part webinar series. The goal of this is to take advantage of all of the projects that we've been working with over the past 4 years that are moving to or towards net zero high performance renovations. And it's taking those lessons learned, matching it up with the building science, and giving it back to you, the audience, so that you can use these tools for your projects. So today we have Mark Rosen, who has been very heavily involved also in all of these webinars from Building Knowledge Canada. We are lucky to have Darrell Paul, who's the technical director at BTRboard, but is very well known for his work with CSA. We have our project teams, the people who are putting this into practice: Robert Klassen, Chelsah Thomas, Trent Doherty, and Dan Cogan. So we're going to get to hear from all of these presentations and panelists. So at this point, that is our team that's presenting here. We're going to turn it over to Kimberly, and we're going to do a couple of polls to find out more about you, our audience. We're hoping to get some more interesting places. We're really putting our bets on whether we're going to get somebody from the territories again. We had a couple of folks from there attend our earlier webinars. And if you're not on the list, please do pop that into the chat. All right, so we've got a strong representation from Ontario, but we have most of the other provinces will still gear for. Oh, and we've got a couple of folks from the US. Great, that's fantastic. Now, what we also like to find out is what industry do you come from? So it helps us understand the different perspectives and the different needs that are coming from the questions that we get. All right. Oh, excellent. Great spread. One of the common themes that we have throughout our entire 4 years of this initiative is the integrated design process, which means we want everybody to be at the table. So this is a great representation. Okay, I'm just going to pause a bit and ask, we were looking to share a glossary of window terms, and I just checking the messages. So Lori and Kimberly, are we able to share that in the chat or the Q&A?
I will add it right now into the chat.
Perfect. So this was a glossary that actually Darrell put together for us using all sorts of industry terms, but it just helps give some context because across different industries and across different areas and regions, some of the terminologies are different. So this is a glossary that will help standardize. So if you're wanting to go back to this webinar and look at what we were talking about, that glossary will help with that. So at this point, I am very pleased to turn this over to Mark Rosen, who is the Director of Building Sciences at Building Knowledge Canada. Mark has been integral in a lot of our, not only our webinars, but in a lot of our CHBA initiatives and moving not only net zero forward, but also the comprehensive holistic view of how we move our existing housing stock to a better future build. Mark, over to you.
Thank you very much, Lynn. Good morning, good afternoon, everybody, depending on where you are in the country. I'm very excited to be here today to talk about one of my favorite topics, windows. I like the description you used, Lynn, of the eyes of the home. We use it in other, pretty meaningful ways too, the windows into the soul, however you want to posit it. I think we can all acknowledge that windows are such a critical piece of our building and home design. They affect us in very material ways, and I think it's going to be a very exciting opportunity today to talk about all the ways that in a renovation scenario, as we move towards high performance, the selection of windows is perhaps even more critical than we at first give it credit. It impacts us in so many ways. So let's get into it right away. We've got a great selection of speakers today, so I don't want to run too long and take time away from them. But why are we talking about windows in this first group of 5 critical webinars about the decisions we're making in our high performance towards net zero renovation projects? Well, first and foremost, it is very, very common for windows to be one of the targeted measures in renovation projects, full stop. They have been sort of a product replacement category for a long time, which makes them at first blush seem like an easy switch. You're taking an old thing out and putting a new thing in the same place. Perhaps you're changing the size of the opening. So they're very frequently targeted in renovation projects. And as we replace windows and improve the performance of windows, they affect us in multiple categories. Not only energy use, which we're very familiar with at this point, but also comfort in an outsized way. Our interaction with the home. Windows are one of the few things that are part of the building envelope that we actually touch and look at and see and use as homeowners. And so the impact on us as homeowners is very real. It has implications for the sizing of our mechanical equipment. That is very relevant in high performance home renovations that are also doing, for example, a heat pump upgrade and might be sizing that new equipment. And of course, the resiliency of assemblies. There are many, many stories we've heard, I'm sure, all of us, about renovation projects where you take out the old windows and discover that the wall is now significantly damaged because of the way the window was installed in the first place. What can we do about that? How can we avoid that sort of scenario as we move forward? It can seem like a lot. So I don't want to scare anyone off before we even get started. Don't worry, we're going to do our best to walk through this and really try to pull something out. what I love about this topic is I think that there will be something in here that will resonate no matter what industry you're coming from, sector. There's something in here for you to lean into and understand more about, and that's always an encouraging thing. We are going to emphasize today the importance not only of good window selection, but of proper installation. And I'm very, very pleased to be followed today by Darrell. If I was going to sit and listen to anybody explain how you should be installing your windows, Darrell would be the one I would want to hear it from. So very cool to have Darrell on the webinar today. And we'll leave lots of time for him to dive into that. I'm going to start us off today by talking a little bit about window selection and some of the criteria that we use as energy advisors involved in renovation projects, but also that renovators themselves or even homeowners shopping for windows would want to familiarize themselves with as they look at the performance of the windows that they're selecting to put into their new homes. When we talk about window performance, we're primarily talking about thermal performance. How does this window react to heat loss and heat gain from inside and outside of the home? And maybe a little bit more nuanced is how is the visible light transmittance and the quality of the build in terms of airtightness going to contribute to the quality of the final install? So when we talk about what makes up the thermal performance of a window, we can improve thermal performance, reduce heat loss. If you hear me say one, you can think the other, by looking at things like low emissivity coatings on the surfaces of the glass. That's often short formed into low E coatings, if you hear that term. Different fill within the gas, within the insulated glass units. Argon is very common nowadays, as opposed to air. Insulated spacers holding the glass units apart from each other. Adding panes of glass. This is very, very, in the public dialogue today. Triple glazed windows versus double glazed windows, triples versus doubles. More glass equals more air spaces equals higher insulating values for your glass units. And not to be forgotten, the frame design and material, which is not even pictured in our little diagram on this first slide, but the frame that holds your glass unit in place and connects it to the wall and the detail around that connection is critical for thermal performance as well as air tightness and water management in a big way. When we start to look at windows and make this selection, there are a number of metrics or numbers that are available to us to help guide our decision making. I'm going to give a very high level overview, and you'll find a lot more detail about these terms in the glossary of terms that was shared in advance of the call and in the chat. But the big ones that matter for this discussion, U factor is the measure of how much heat is lost out of a window. And it's the inverse of R value. R value, I think we understand, many of us understand intuitively, is the resistance to heat flow. U value is the opposite. It is the ability to enable heat flow, if you will. And so where we want higher R values in our walls, we want lower U values in our windows. Lower the better. And to make the transition, you can actually just, there are formulas to convert one to the other. That's U factor. The second number that's really, really important is the solar heat gain coefficient, or SHGC, of a window. We all know what it feels like when you stand inside your home and the sun is shining through and the floor is warm and it's lovely. You feel this radiant heat on you, or this direct heat coming onto you. That is a direct result of how much of the sun's energy is being allowed to pass through the glass of that window and come into the space within the home. And so when we start to talk about not just the lovely ambiance of having the sun come through your window and warm up your floor, but rather what is the impact on your cooling of bringing that heat into the home? What is the impact on your comfort of bringing that heat into your home, often in very quick spikes when the sun comes out? Solar heat gain coefficient is our tool for mitigating that. Higher numbers, it's a scale 0 to 1, higher numbers will allow more of the sun's energy into the home. Lower numbers will resist more of that sun's energy coming into the home. Visible light transmittance is also communicated. That's just a measure of how clear the glass is. We can get into that in a little bit more detail when we get further into the presentation. But there's a fourth one that appears on window labels that you should start to be familiar with, and that's called the CSA, or the energy rating, CSA energy rating. And the energy rating is a single number that was developed in an attempt to give builders, renovators, energy advisors a very easy way to appraise the value of a window from an energy performance perspective. It combines the quantified impact of solar heat gain coefficient, U factor, air leakage into one number using a formula, and the higher the number, the better the quote-unquote energy performance is of the window. However, I draw your attention on this slide to the text in red. The energy rating is really focused on the energy performance of the window in the heating season. And that is because having a high solar heat gain coefficient, which allows more of the sun's energy through the window, improves the energy rating score of a window. There may be situations that we'll see in a few slides here where you don't want to capitalize on a lot of the sun's energy coming in at unexpected times and influencing your heating design and your comfort in unexpected ways. And so I will hopefully start to convince you today that U value and solar heat gain coefficient should be your starting points for evaluating your window selection in priority over the energy rating of the window and the number that you see there. Now, all of these numbers are available on the stickers that are mandated to be applied to the windows that we buy from suppliers and manufacturers. So they're highlighted here on these few slides. Window labels come in multiple different formats. So you might see some variety, but here you can see the U value is very clearly indicated on all of these. The example on the left actually gives the U value in imperial and metric U values. So you need to be aware that there is a difference here. I've made the mistake myself where I've read an imperial U value, thought it was a metric U value, and thought that I'd found the world's best performing window and been really excited for a minute and then realized my mistake. So make sure you're comparing apples to apples with your units. Of course, all of our Canadian building codes will reference metric U values when you're making your selections. Next to that, very clearly, we see the solar heat gain coefficient listed as a decimal, again, between 0 and 1. A score of 1 would be equivalent to allowing 100% of the sun's energy through the window into the space. A score of 0 would be an opaque window, one that doesn't allow any of the sun's energy into the space or rejects an equivalent to no energy. You will not see a 1 or a 0 ever. Typically, we will see numbers that range between 0.15 up to 0.6, 0.65 sometimes, depending on your climate zone. Below that, you have visible transmittance, and this is something that I typically recommend to people not to be too concerned about. Unless you have two windows with very different visible transmittance values right beside each other on the same wall facing the same way, it is very difficult for our eyes and the way our retinas adjust to variations in light to actually see a difference here, unless you get into very low numbers of tinted glass. So don't worry too much about this number. You will see a relationship between visible transmittance and solar heat gain coefficient, but don't dwell on it too long. And then the energy rating score will be on there as well. Something that is very useful in our industry is to get really good at reading window quotes, and manufacturers' quote sheets will also provide this information for you if you start to know where to look. So here is an example of a quote for a single window, providing a ton of very complex and dense information, but right down at the bottom, you can see that this is an Energy Star qualified window with an ER rating, a U factor, and a solar heat gain coefficient for your appraisal as you're evaluating this quote. The Energy Star brand is also available for windows as a product. This is very helpful because the government actually has a product list, a searchable product list, and I'll have a slide at the end which shows a link to that. But just for reference, the benchmark for Energy Star windows is a U factor of 1.22 or lower, or an energy rating of 34 or higher. Remember that those metrics are inverted from each other. But they also have a better performance category, an Energy Star most efficient window category, where the U factor target is more aggressive at 1.05 and the ER target is higher at 40. Those type of numbers that you see for most efficient windows really start to be predominantly triple glazed windows. This is right around where the tipping point tends to be in the manufacturing of windows. So what do we do with these numbers? When we see that when we hear someone like me talking about, well, use the solar heat gain and the U value to pick your windows, well, what am I looking for with those? Am I always looking for a lower U value? Am I always looking for a low solar heat gain value? What is the difference? These slides will be shared afterwards, so I encourage you to dive into these more complex tables in more detail on your own time. But I want to draw your attention here to a case study home that was modeled using 3 different U values of windows, 1.6, 1.44, and 1.2, and 2 different solar heat gain coefficients for each window. Sorry, I'm trying to control this. There we go. And what you can see here is that the energy consumption of this archetype home using a 1.6 U value window and a moderate to high solar heat gain of 0.4 achieved the same energy performance as a better insulated window at 1.2 with a lower solar heat gain coefficient of 0.19, meaning it was rejecting more of the sun's free energy in this scenario. So energy consumption is the same. Now, there are lower numbers on this chart. So if you were being driven solely to select your windows by saving energy, this might not be the number you gravitate towards. You might be gravitating towards this 98.8 that you see where the solar heat gain is higher. However, as we make decisions about the solar heat gain coefficient, we have a direct impact on our mechanical system sizing calculations. And in that previous example, the difference in energy use was negligible, but the difference in cooling size could be as large as 1 ton or more. Here we can see on the left that the 1.6 low gain window versus the 1.6 mid gain windows had a 10,000 BTU per hour cooling load difference in the same home with the same size of windows. So it's a balancing act. We're not only looking for energy savings, we're also looking for mechanical system sizing efficiency and the impact on our comfort in our homes. And this is a bit of an area of new understanding that we're really trying to grapple with as we move towards this heat pump landscape, if you will, heat pumps coming in and offering both heating and cooling performance. And we're trying to balance those with our window design. That being said, there's an opportunity here to a bit of a shout out to the integrated design process that Lynne mentioned earlier today. It's very important as you plan your renovation project that your mechanical designers and contractors are aware of what your window selection plans are, so that as they're recommending a sizing of equipment, they're using the right numbers for their solar heat gain assumptions and their U value assumptions. Another thing that starts to be very interesting in existing homes and renovations is that as you change windows and reduce cooling loads, here we can see a change in window from a base window of 1.6 and a high solar heat gain to a high performance triple glazed window with a U value of 0.9 and a solar heat gain of 0.2 is not only 1.5 tons less cooling, but it's a smaller main trunk size. So if you're looking at gaining some headspace in your basement and redoing your ductwork to do that, here is a 24 by 8 main trunk as opposed to a 28 by 10. And we know that every inch counts in older homes and basements when we're trying to renovate those homes. Who would have thought? You're looking for ceiling height in your basement, you should consider what choice you're making for your windows, right? Something kind of interesting. Something else that really guides us when we're making decisions about our windows is what is the ratio of window to wall in our home? Do we have lots of very big windows? Do we have fewer, smaller windows? And knowing which end of that spectrum we're on can actually sometimes guide us to prioritize a window upgrade over a wall insulation upgrade, or perhaps if we're doing both, to decide which one we're going to do first. This chart shows 2 lines and the impact on the overall thermal performance of the home's envelope. The double glazed window in lighter blue is the top line at the left, and the triple glazed is the bottom line at the left. Across the bottom axis of this chart is the fenestration and door to wall ratio number, which is basically the percentage of your walls that are not walls, that are windows. And you can see on this chart that at about 17% window to wall ratio, there's an inversion where making an upgrade to your windows to triple glazed is actually more impactful than adding R10 sheathing to all of the walls in terms of overall thermal performance. And you can see that in a little bit more detail on this next slide, which compares on a single reference house in this case, the energy savings associated with making a U value improvement with a moderately low solar heat gain coefficient compared against different levels of continuous insulation to your walls. And in this example, because the fenestration door to wall ratio was 20%, on the right side of that crossover point, the window upgrades save more energy than the wall upgrades. Now, that's not to say that you should choose one or the other if you have the option of both. There are many good reasons to do continuous insulation on walls that we looked at in the webinar on exterior walls, but it's an interesting sort of switch of mindset, where there are other reasons to prioritize perhaps phase one, do your windows. If it's matched with the heat pump sizing, there might be a lot of good reasons for that to be considered. Sorry, I'm in trouble. Last two slides before I hand it off to Darrell, but this is also a topic area where we are hearing a lot more discussion about embodied carbon, and really specifically about the trade-off or the payback of operational carbon savings versus embodied carbon spend. We've heard from many people questions around, is it worth doing a triple glazed window, adding an extra pane of glass because there's embodied carbon in that glass? We know embodied carbon now is something we're trying to reduce, use less of in our homes. I want to make a good decision. Should I do a double glazed window and save on that embodied carbon? Well, I think, that question comes from the right place. But what we can see in this little example, that a home with 20% window to wall ratio, to go from doubles to triples would have to spend about 0.7 tons of embodied carbon, not an insignificant number. However, the savings on this example home, which I believe was a traditional furnace operating, but a reasonably high performance home, was a savings of 0.9 tons of carbon operationally every single year. So the payback on that carbon spend is less than 1 year return on carbon investment, if you will. And for the remaining 49, 79, 119 years of that home's lifespan, it's going to save that much carbon again every year. So be aware that it's a balancing act in all these things, right? This is the complexity that I sort of hinted at the beginning of the call. Don't look in one category for your decisions, but rather consider the balanced impact of your windows, because the opportunities like that will arise frequently. And lastly, comfort. We can't talk about windows and not talk about their impact on comfort. And this case study is one of my favorites. This was one that was done, actually, I believe the anonymous individual in this example is Rachel Oding, Andy Oding's partner. And we were looking at the impacts from a comfort standard using ASHRAE 55, a comfort standard, on the impact on an occupant sitting 1 meter from a patio door, and trying to determine how many hours of discomfort there were using single, double, or triple glazed products. So we looked at the winter condition and the summer condition, and with a single metal frame patio door, maybe what you find in the home before you start renovating, in the winter, there was, by the standard, more than 3,000 hours of discomfort, and in the summer, more than 300. I would suggest that anybody you're trying to sell windows to would find these to be unacceptably large numbers of hours of discomfort. Upgrading to doubles helps. A double glazed window, kind of an available off-the-shelf product with a fairly high solar heat gain coefficient, reduce those numbers by a lot, but still 500 hours of discomfort in the winter and more than 75 in the summer. Look what happens when you go to the triple glazed window. At a U value of 1.2 or lower, with a low solar heat gain coefficient, the discomfort in both the heating and cooling season was negligible. What an amazing performance and experiential upgrade for the homeowner to have, to be able to now sit beside the biggest window in their home and enjoy the experience rather than suffering through the discomfort. So there we go. We've got energy considerations, we've got carbon considerations, we've got cooling load considerations, we've got comfort considerations, and all of those things will play into our decision matrix as we make our window selections for our renovation projects. This slide, the last slide I'll leave you with, has a link to NRCan's searchable product list database. And here you will find every Energy Star rated window product that they have on file to help guide your starting point. As you reach out to manufacturers or decide which manufacturers to reach out to, we find a lot of EAs and renovators and homeowners will take advantage of lists like this to do exactly that. Now, everything I've just told you about how to pick the best windows for your project will not matter if you install it in a wall that rots or that the wall will leak water into the home and the window will have to be replaced in 2 years. So I'm very, very happy to introduce Darrell Paul to you. As Lynn mentioned, Darrell is with BTRboard, or I don't know, Darrell, do you shorten it to Better Board or you prefer BTRboard? I'm not actually sure.
Yep, you can call it BTR board or better board.
There you go. Either one is good. But Darrell has also been intimately involved in the CSA A440 standard development, which is a standard that governs, not governs, let's say, really speaks to the best practices in window installation. And beyond a standard that outlines that for us, Darrell is very familiar with how to go beyond that. How do you do even better than what the standard says is the minimum requirement? So Darrell, I'm very, very happy to hand it over to you to take us through what we should be thinking about when we're installing the windows we've just put all this brain power into selecting into the walls and the projects that we're working on. Over to you.
Thanks, Mark. And welcome, everybody. It's nice to be able to talk to you about a topic that's near and dear to my heart. I've spent, I guess, the better part of almost 50 years in construction. Spent 12 years as a framer, a site supervisor, and then 25 to 30 years, depending on how you count it, as an envelope engineering consultant. So, although I'm not an engineer, I had a bunch of engineers working for us, but we spent a lot of time diagnosing and testing how we do things. So, oops, let me just get back here. So when we talk about doing window installations and detailing window installations, there's a few things that we need to think about. So, we talk about detailing, making sure we get it right. But before we start, what are the keys to make sure that we're going to have a successful installation, we're going to have a comfortable building, and it's going to perform long term? Well, one of the things we want to highlight is to make sure that you understand that this isn't an installation guide that we're going to be talking about. This is about how the system is going to perform. So the system performs by putting an opening into a wall, which has some components in it, and then we throw a window in, and that really makes a difference in how the building performs. So I always like to start off with a bit of a shocker. When you look at buildings like this and you look at the deterioration on the walls, what's the cause of this? Well, in most cases, the cause isn't the actual window itself. The cause is coming from the fact that, the window was put into an opening and then there was some assumptions that were incorrect. So for instance, there's 4 points there. The exterior sealing alone prevents leakage. Well, that's an incorrect assumption. That's false. So there's a lot of people that feel, let's put the window in, let's seal it up, but we can create problems with that. So we're going to talk about that. The rough opening will never see water. And again, that's false. Water is going to get into that rough opening, whether it's from incidental moisture or whether it's from condensation. At some point, you will have moisture in that opening. Another one is that air leakage is actually beneficial for drying. And that's actually, in a cold climate, particularly in Canada, that's actually false because air will dry things out. But when you transport humid air from the house into a cavity, you create condensation and frost. When you transport air from outside during rainfall, it will pull that liquid into the wall cavity or into the window rough opening. So that would be a false statement as well. And then all insulation improves performance. So a lot of people feel that, as long as you take spray foam and you spray foam the rough opening, that's going to improve the performance of the building or the wall, especially when it comes to the window. And that's actually false. We find that in a lot of cases, the spray foam inhibits and creates problems. So, what are some good techniques and ideas and challenge or methods that we can have a system perform correctly? So, let me just find the play button here. Now, hopefully, this plays on your system. This is a wall assembly with a window in it. You can see that they've got some blue skin material, some self-adhered membranes. But notice underneath that the deterioration and the damage that's occurred on that wall. Now, what's the cause of that? Well, obviously it's gotten wet and it's gotten wet repeatedly and over a long period of time. So the deterioration has occurred because water has gotten in there. Now, you saw that it was sealed around the perimeter, but does that take care of it? Well, not necessarily. So once the water gets in there, what are we doing with it? When we look at the source of the water, there's an incredibly high percentage of water that gets into a rough opening that comes from well above the window. So you can see in these infrared images of water testing that was being done, how the water is getting in from an upper source. So once it's in that rough opening, it just runs around that rough opening, down the sides, and sits on the sill. Well, if you don't have any protection at the sill, what protects that bottom, rough piece of lumber from soaking up the water and deteriorating over time? And worse than that, when you think about you're adding insulation to the exterior, let's say you're putting a layer of continuous insulation or you're improving on the air tightness. Well, even in the summertime when you would expect, some drying potential to occur as the temperatures warm up and the humidity equalizes, you're not getting that because the wood is so saturated and soaking wet. For some of you who have taken buildings apart, you find that a lot of times that the damage is irreversible. You have to go back in and do a lot of retrofit and replacement. So that takes us back to this statement here. Before you start a window replacement, what are the keys to understanding how to properly detail a window? And particularly if you're looking at adding a window into some complex situations. So, for instance, what's the cladding? What's the material that you have to remove to replace that window? Is it an old window? Is it a reasonably new window? Does it have flanges on it, or is it a box window with no flanges? These are all questions that you have to answer. So that is part of the discussion that we're going to go into today. But really, we want to find out what are the principles that we can learn from, because we can find all sorts of, how to installation manuals on how to replace a window and install a window. But if we don't understand the why, all the years that I was in construction, particularly in framing and in site supervision, if I didn't understand the why, I tended to look at it and go, well, okay, I'll do that, but why? And I remember I'm thinking back to things that I've done that are just ridiculous that I actually did them, but because I didn't know the why was one of the reasons I did it. So let's start with the four control layers. So in building science, we always talk about four control layers. We talk about water control, and you notice there we don't talk about stopping water. We talk about management. So we're controlling or managing the water. We talk about air control. We talk about thermal control, and we talk about vapor control. These are the four critical control layers that we need to address as a system when we're changing windows or adding windows or reinstalling windows. And I think of it as a window replacement being like a transplant, right? You have four of these control layers to deal with. There, you always have water, rain hitting the building. You always have air that's trying to push or transport moisture either into the building in the summertime or out of the building in the wintertime. You have thermal control, so insulation, which reduces condensation potential. And then you have vapor control, which of the four of them, vapor is the least concerning issue here because most of the time, vapor by means of diffusion is more for a drying potential than it is for a wetting potential. So if we look at the four control layers and we put them into context with the building itself, here we have a building, we're removing a window, and we can see those critical layers there or the critical control systems, water, air, thermal, vapor. Each one of those is connected to that window that we're removing and then want to put back in. Now you'll notice in the red line there, the water line, we're looking at a first and second plane of protection. So there's actually two parts to this component. We have the first plane of protection, which is what the building code refers to as our cladding, our caulking that we put around windows, the window itself, the flashings, all of those kind of, take the water and deflect it away from the building. But then we have a second plane of protection, which is hidden in behind. That's our weather barrier, our WRB. So our weather barrier picks up and collects water that gets behind. It drains it down to the flashing, and that takes it back outside. So when we look at second plane of protection, we can't just look at it in terms of what happens behind the wall. We have to look at in terms of what happens in the rough opening of the window. So that's the first thing. So to help us understand that, let's have a look at a cross section of a window. So here's a typical flanged window. You can see that it's got a couple of components here that we need to focus on. So let me just find a pen. And it's not coming up. There we go. One of these buttons is a pen. Nope, not that one. All right, let's just walk through it. If you look from the right-hand side, you'll notice it lists the exteriors on the right-hand side. You've got rain coming down. You've got first plane of protection, which is the cladding. You've got second plane of protection, which is the WRB. And notice the drainage lines that you're seeing there. So if you look at the far right drainage lines, water's hitting the window. It's running down over the window frame. It's running down over the flashing, the siding. It's keeping the majority of the water out. So we're deflecting as much water away as we possibly can. Then the second line that you see that goes underneath the two glazing stops there in the triple glazed window, the three panes of glass, you can see there. You've got window glazing. Here's my pen. Found it. Right up here. You've got windows that have glazing, but the water can actually get in and around the glazing. And the reason for that is when the wind blows and the glass deflects, you have these rubber seals here that could possibly open up and let water in. So all our windows have this backup system that lets the water drain back out, hence why we see the weep holes or the drainage ports on a window. And what that does is it takes the water that gets in there and diverts it back outside. Now, with these little cavities, these little compartments that we see, those are actually little insulators. Those are no different than your fiberglass insulation. You're compartmentalizing that dead airspace so that when there's convection in there, it's not moving from one side to the outside or to the other side, right? Not from the cold side to the warm side. You've blocked those out. So fiberglass does the same thing. It just makes smaller compartments. So as you're looking at that, then the next part that we need to look at is right down here in the rough opening. So right here, we can see that there is potential for water accumulation there, and that can come from upper parts of the wall and the house. That can come through the rough opening, down the window, and collect at the bottom. So right here, this black line is our sill pan protection, protecting the rough sill. And it's directing the water back out and down and away from any sensitive materials. So ideally, that's part of our second plane of protection, and that kicks the water back out to the exterior. So when we look at that, we have a couple of things here. One is we have a bit of a back dam created by the closed cell backer rod here with a bead of caulking here. And that actually helps also not only with moisture, but that helps with air. So whether we're putting in a flange window or whether we're using, say, a non-flange window, a box window like you see here, the direction of the water flow is going to be from the outside when the rain hits. It's going to also be from that cavity that's underneath the glazed units, and then also from the rough opening. And we're taking any water that gets in there when we're dumping it back outside. Now, we talked about water being important. So first, second plane of protection, deflect the water away from the exterior of the unit. Water that gets in, we collect it using the second plane of protection, something that's water resistant. And if it's horizontal, it should be waterproof. So water sitting there doesn't soak through the material. But then notice down here, we're talking about the window air barrier. So what is the air barrier and where does it fit into the window in this application? Well, almost equally important as water is the air barrier. And let's illustrate it this way. When you look at a car door or a trunk, what do you notice about where the seal is on those components? Well, first of all, you notice that they don't try and seal the exterior of the door. They leave a little bit of an opening there, small opening. So picture driving down the road, you have a small opening. The wind is blowing, creating a pressure. It's going into the opening, but how far can it go in? It can only go into where the weather stripping is. So here's the weather stripping on the door. And the reason that that's inboard is because the amount of liquid that would hit the surface on the outside is significantly higher than the amount that would hit the weather stripping on the inside. So if we could simply look at our opening in our window and say, okay, here's the outside where this opening is, here's the flange or the exterior component of the window. As we try and push air into that, it creates a high pressure. And because the backside of this window is airtight, or the backside of this door that we're looking at is airtight, then it just creates a higher pressure inside here. Once that's full, no more air gets in. So think of rain coming down here and trying to get into that bottle. If it's already full of air, no air gets in, which means it can't transport any more moisture in there from rain. And if you look at it from the opposing side, it's the same thing. So you're really blocking and preventing air from getting in there by means of a pressure equalization system, which is similar to what we use in a rain screen or a drained and vented airspace. It's the same principle. So now, if we take that principle and apply it to something like a window, and we look at this window here, this is a window under air pressure, so we've got a blower door going. But you notice there that where they've attached the jamb extension to the window, there's a significant amount of air being drawn in, and at the casing underneath, there's additionally a significant amount. So from the standpoint of water or vapor, if there's an air transport, air is flowing through that assembly. As it flows through, if there's humidity in it, say for instance, a higher pressure inside and outside, which can happen due to stack pressure, can happen due to wind, that could be on the leeward side of the building, or it could also happen from mechanical pressurization. Maybe your HRV is not balanced. So it's pushing air out. Well, as soon as it goes into that cavity, obviously there's enough space for air to move there. You can get a tremendous amount of condensation and moisture building up in there. If you're going from the opposite side where it's raining, well, when the rain is coming in, as it runs down those surfaces, if the wind is being pulled in, that can also pull water in. So again, you want to stop the transport of, what are we transporting? It could be humidity, it could be water, but it's all about a pressure. So when we apply that to a window and we look at a pressure plane on a window, here's what we see in section is the fact that over here we have, you can see these green lines, we have the pressure drop or the line of the pressure plane here. We let the air equalize in pressure out here in this yellow area. It equalizes up in here because once it's full of air, no more air comes in, which means there's no pressure change right here at these openings. And there's no pressure change right here at where these flanges meet. So whether it's a flange window or a box window, a non-flange window, doesn't matter. If there's equal pressure right here at this cavity as there is outside right here, then we have nothing pulling water into the cavity. So you'll notice on this typical example, we've got an R20, R22 pad of insulation. We've got the poly on the inside, the 6 mil poly, and the line of pressure is always away from where the water is. So it's neutralizing the ability of the air to pull that rain, that moisture in there. But in the meantime, if we do get moisture into the rough opening cavity, it's sitting on a protective water-resistant sill pan. So this is the important part when we're putting a window in, is making sure that the water that gets in has somewhere to sit safely until it can drain back outside. And that's the problem with older windows and older installations, is a lot of times that water was left to sit there and it had nowhere to go. All right, so there's some of the building science. We talked about the 4 control layers: water, air, vapor, and thermal. And we've talked a little bit about the first and second plane of protection, but let's go back to the rough opening. So here we're back to a rough opening. Maybe you've stripped the entire wall, maybe right down to the framing, or maybe this is what you need to envision as you're doing the construction, envisioning what's behind those walls. So you have a lintel or a header, which supports the opening, transfers the loads from the middle down to the sides. You have a rough opening, which gives you the size of the window plus a little bit of space around it. Realistically, what that's for is shifting and movement of the wall so it doesn't crush or damage the glass or the glazing or the window itself. And gives you a little bit of space to provide that air barrier and some insulation around the window. But then you also have the rough sill, and the rough sill is what suffers most in existing homes when there's no protection. Now, if I take it one step further and I say, okay, so from that rough opening, let's install a window. We're still talking about structure. What is the weight of this triple glaze IGU? Well, if that's in the 200, 300, even 400-pound range, how do you transfer the load from that glass through the actual window and then through onto the framing? And this is another problem that we run into, is that when people put these shims, these blocks to support that window, they need to level those shims before they set the window in. Because if you don't, if you put the shims in, set the window, and then level the window at that point, would you come back and put another shim in there to take the load or the weight? And in a lot of cases, the answer is no. So a lot of people don't level those in there. My preference is that those blocks, those supports should be structural. They should be water resistant or not damaged by water. You can see that these are preserved wood here. You could use a plastic one, whatever. And that's supporting that so that it doesn't crush and you lose the seal on the window. So now you're not just dealing with water coming in through the rough opening, you're dealing with water coming in through the window. Your next layers are your moisture control components, right? You have your first plane of protection, which is your cladding. You have your second plane of protection. But remember, you need something in that rough opening to collect the water and drain it down to a waterproof or water-resistant sill pan, and then allow that to take the water and drain it back outside. So these are your main components of your moisture control section when you're putting a window in or you're reinstalling a window in a renovated wall. Another aspect that's important is, the fact that some of the weather-resistant barriers are not overly resistant to long-term water attack. So here's a piece of tar paper. This building that we took apart was approximately 10 years old. This is an absorbent material, so tar paper is absorbent. You'll see it on there as a 20-minute, a 30-minute, a 60-minute tar paper, so it absorbs water. But over time, if water is consistently running on it, it's just tar soaking into paper. So as the water runs over it, eventually that tar gets washed out and you're left with paper, which is what's causing deterioration here. So you could use a non-absorbent, like a house wrap, a synthetic material. But one of the other things to keep in mind with the synthetic materials is you'll notice down here, and this is a great illustration out of the document that's coming up, that basically when you're looking at materials like stucco or materials that can absorb water, when those get into a situation where the sun is beating on them after a rainfall, if they have really high vapor permeance, and we always talk about this as being better in a house, we want to have a house wrap that's really high vapor permeance to let lots of vapor through. The problem is we get the reverse action. We get a solar vapor drive. So it forces water and actually steam and pressure through the material and into the wall where it gets trapped. So you'll notice down here that we actually want something in the medium to low perm rate to resist that moisture coming back in. Now, it really depends on where you live. If you have high humidity in your area, if you're in a dry climate, that's going to affect that and change it. So I guess the point that we want to take away from this is remember that the climate that you're building in, the climate that you're putting things together in, is what you need to assess what materials you put into that system. So this is just one part of the system. This WRB is part of your second plane of protection. How does that perform long term so that the water that gets through it can still have somewhere to go safely and doesn't build up and accumulate? So there's nothing wrong with moisture getting through a material. It's just how much moisture and can you get rid of it quickly enough? So that's another aspect to, putting second plane of protection in. All right, so let's think about now, we've talked about the technical side of it in terms of just straight installation of windows. Let's think about it now in terms of replacement of a window. If you have to take a window out and replace it with a new window, what are some of the challenges that you're going to face, particularly in a renovation condition? Well, first of all, most houses are atypical. In other words, they're not going to be standard. And the reason is, at least from my experience, when you take an older building apart, how often has it been renovated? How often was the window a standard size, or did somebody get a window that was a custom size? So you might have unusual framing. You might have window sizes that are way out of whack. You might have layers in there that you never anticipated. And maybe past renovations have changed the wall. You also have to look at the original construction era. So buildings built in the 1940s, 1950s, those are going to have fir construction versus spruce construction. How does that differ? Well, some of those things are very important to understand in terms of when the building was built. 30 to 70 years of changes are going to impact how that building was done. Maybe it's been renovated more than once, maybe several times. And then the other big one is unseen damage to the framing. And you may not notice that until you actually rip that section out. Even if you're just doing a pocket window installation where you're removing the frame of the interior and leaving the actual jamb of the window and the casing in, you still need to identify, is there unseen damage to the framing in and around that window? Because there's nothing worse than putting new windows in, and then a year later, you start to see failures on the exterior or the interior of the building because water's already getting in from another source near or around what you've identified. Now, here's a resource. If you take a picture, I'll give you a minute here to take a picture. This is a QR code. This is a fantastic document published by BC Housing. It's called Best Practices for Window and Door Replacement in Wood Frame Buildings. And this book gives you all kinds of information on replacement of windows. And if you don't get it, that's fine. We'll put these up later and we can get you this information as well. I also helped work on this document here, CSA installation document. So CSA A440.4 is the window install document. CSA has put a very simple, straightforward installation resource for flange windows and a whole other section for non-flanged or box windows on their website. So you can just look that up. You can hand that, web link to your framers and they can install it and you'll be able to put those things into practice by just simply sharing it. So just to give you a few examples of what we're talking about here, when you look at window installations on brick, it might be easy to access this location if you're using an old aluminum clad window. But if you look at this location here, how are you going to get that window out and not damage the stucco? So when you're looking at things like stucco replacement, what are the 4 control layers you have to deal with? Where's the first and second plane of protection? How are you going to reintegrate those? Those are questions that this document really answers well. When you look at things like brick and then wood windows, how do you deal with a wood window installation? Or how simple is it to take lap siding off and replace windows? It's significantly easier to do than it is to, say work with stucco. So this is the kind of details that this document provides. When you look at something like this was an article in Fine Home Building magazine, and they were showing, when you're taking a window out of an old brick building, you can see that down here at the very bottom, you have that space between the two. And then you're going to be able to, see where you need to make that tie-in so that water that's being drained off the window or the roof opening can drain down the outer face. So those are some of the details that this document is going to provide for you. So, we don't have time to go into all those details, but just to wrap up here, this is another example of, various construction methods. When you look at older windows like this and how you had lath and plaster on the inside of the walls, and you had these old fir windows, and you had fir construction, which was pretty durable. These are the things that you're going to find in older buildings. And then as you move up through the years, you're going to see things change. You're going to see a little bit of insulation into the walls, which is going to affect its drying ability. You get into newer walls, you get into higher insulation, vinyl windows, different things like that. And then you get into more modern where you have the option of either using a flange window or a brick mold window. And then on the other end of the spectrum, you have the non-flange windows where you can insert that window in different locations. So these are very good ways to look at, what's some of the options, some of the things that you have to do. Pocket windows are inserts that can be put into the opening without having to remove the actual window. You can see here you've got old aluminum windows. So those are things that you can keep in mind as well. All right, so we're going to wrap this up with just a couple of tips here. Um, we've got a couple of checklists here. One is a key takeaway is make sure that where you're building, you consider the environment. So even though a lot of the materials and the components are given to you for Canada, it's going to be different in one part of Canada than it is in another part of Canada. So make sure you look at the climate and the exposure in terms of how this system is going to perform that you're putting in. Think about the materials that you're using. Checklist two is how is it going to be different putting vinyl siding or replacing vinyl siding than replacing stucco? How are you going to deal with flanges that are buried behind? How are you going to deal with situations where you have brick and maybe the brick is deteriorating and you have to replace it when you're putting windows in? So here's another good checklist that'll help you there. Checklist three is all to do with water and making sure that second plane of protection is picking up the water, collecting it, holding it, and then dumping it back outside. Checklist four, make sure you understand what you're getting into when you start to open a wall up. You're going to have potential damage. So be prepared. And then finally, the key takeaway that you want to have is remember the building science, the four control layers. Control the water, which is broken into the first and second plane of protection. Control the air, manage the pressure just like you would with a water bottle trying to blow air into it. If you have a good water bottle, you can have that hole in the end, but the air compresses in there, compartmentalizes, and then you don't get any more. Thermal control and vapor control are important, but not nearly as important as those top two. So that's the end of my presentation. So we'll turn it back over to Lynne.
Thank you so much, Darrell. I'm looking in the chat and I want to call out this one from Stephen Thwaites. When Darrell says he helped with the new CSA window installation standard, it's like Connor McDavid saying he helped Team Canada. So a great shout out, but great visuals and a great walkthrough of that why. And it's understanding that is so critical when you have your crews on site. When we send this out, make sure you copy this presentation, take it to your lead carpenters, take it to your site supers, and have them have this on their iPads or stapled up with the plans and elevations so that they understand the why behind all of this. Thank you so much, and thanks to Mark for laying the groundwork of that building science behind there. So at this point, what we're going to do is we're going to turn it over to the project teams. And if you've noticed in the Q&A, Toby Smith from Building Knowledge, who has been our lead EA program manager for the entirety of this Towards Net Zero Reno initiative, has been answering questions, and we're saving some for the Q&A. But at this point, I'm going to turn it over to Robert Klassen, who is the owner of Livingstone Eco Homes, and Chelsah Thomas, who is the Net Zero Energy Advisor. And for those that are just new to this Towards Net Zero Reno initiative, every single one of our projects in this initiative was assigned a qualified net zero energy advisor that this NRCan funding helped to support so that we could have that integrated design knowledge and all of this education brought to this. So at this point, I'm going to turn it over to Robert.
Hello, I'm Robert Klassen. I run Livingstone Eco Homes, and this was a net zero ready project. We are in the process of just finishing up. Coincidentally, this also happens to be my place, so I can also speak to it from the perspective of the homeowner and the lived-in experience of having better windows. And one moment, technical difficulties.
You know, it might be left on the pen on the annotate one,
Okay,
but
let's see if that's
by
an
the
issue
keyboard.
here. Okay. I'm not sure if that, no, you're right. Oh, there we go.
There we go.
All right, so there's a quick before and after. It's a 70s bi-level in southwestern Alberta. So we're in a zone 7B. Uh, we are lucky enough to, in spite of that, we have rather cold weather. We do have decent sunshine in winter. So choosing the right windows was going to make a pretty big difference in the project. Another before and after shot. In addition to swapping out the windows, we also did cladding upgrades and significant envelope upgrades as well. It was kind of did all the things all at once. The things we're really trying to achieve with this project, in addition to the obvious improved energy efficiency, we wanted to explore and test drive different ways that we could do that affordably and also in a rural application where there's less material availability, less technical skills readily available, while a lot of net zero happens in an urban context. There is a percentage of the population that lives far from town, and we want to make sure that a high performance building is an option for those people too. Another thing that we did was we lived in the house through the renovation. That made some things more complicated, but it also improved the affordability of the project because we did not have to pay for a place to stay at the same time. Some of the top upgrades that we did was we put extra insulation on the main floor, increased the insulation in the attic, spray foamed the basement walls. There was also a heat pump installed, a heat pump water heater, and we did aero barrier to make sure that we really had that tightness taken care of. But for what we're talking about here today, the biggest difference was that we installed triple pane windows. And again, technical difficulties. Some things to mention about this, and I'll get Chelsah to chime in wherever it makes sense here, because she was involved in the process as well of making the best window selection. One thing that was obvious was that for my particular application, it made a big difference for sizing and for window selection, whether the window was south facing or on one of the other walls, and what sort of overhangs we had. In my case, because my glazing ratio is relatively modest, I wanted to max out my solar gain on the south side, but all the other windows have coatings on them to maximize the reflectivity. So basically there's less energy transference. They have a lower solar heat gain on all the windows except for on the south where we maxed out the solar heat gain. On a reno, because we had existing window sizes, even if we did make the windows a bit taller, we stayed at the same window width. So we didn't have to modify lintels and jack studs and other structural things. And that kept the renovation a little bit more straightforward, which was important for affordability. And we also wanted to maintain the relatively modest glazing in part because it is public street facing for privacy reasons, and also so we could install it without needing to bring in heavy machinery just for that. I selected the windows off the Greener Homes list, but we did actually look at several different window packages. Chelsah was involved in helping to pick out the one most suitable for our application. But one takeaway was that regardless of which package we went with from different manufacturers, as long as we picked the best one they had on offer, it would have been viable. So that's good news for people in less urban situations who have less product availability. there will usually be some option that can still get the job done. Any thoughts on that, Chelsah?
No, I'll be expanding on those thoughts here shortly.
Okay. This might be that spot.
This is, yeah. So, yeah, Robert and I spend a lot of time thinking about window selection, probably him more so than I was, but this gave me the opportunity to really dig into a micro project within the scope of the larger project, specifically looking at the different choices that a consumer like Robert or a homeowner would go through when choosing windows, and how myself as the energy consultant can assist with that process using data analysis. So the intention was to use all the information we had at hand to make the best decisions possible. What we were dealing with before the renovation was typical double pane windows. They were leaky. As you can see in the image, there was condensation. And Robert could probably speak to how uncomfortable certain rooms were, or maybe the house as a whole, with the double pane windows. So we had about 5 different window packages that he presented, from Plygem to Geldwin, Lux, All Weather, really easy to access across a wide variety of suppliers. And then he provided the cost differences between the window packages. And, you know, we're talking about doors as well, but the doors had less of an impact than the windows specifically. Performance upgrades like windows are usually extremely costly for homeowners, and the window performance and the cost can vary greatly. So we had this unique opportunity to view this project through the lens of both the homeowner and the renovator in relation to these upgrades. So as a renovator, I'm sure, I don't want to speak for you, Robert, but you were factoring performance in. You were also trying to meet the technical requirements of the Net Zero program, ease of installation, and accessibility of the product, as we mentioned. But it was also important for you to be able to replicate this project across similar houses in your region, so that you can serve additional clients with another net zero renovation. And it was a big factor. So on the homeowner side, he wanted to improve the comfort, reduce condensation. We wanted to consider long-term operating costs as well, and overall be able to afford a net zero renovation. So the final results of the project, as you can see here, is a 74% improvement in total energy reduction and a 5% reduction in greenhouse gas emissions without solar added. So solar is planned for the future, but impressive results nonetheless where we started. If you can hit the next slide, please, Robert. So in our model, there were some design considerations that we had to adapt for while planning, including the fact that the house has a ton of south and west facing exposure with varying sun protection. Although he did plan a heat pump for cooling, we wanted to consider the opportunity to balance cooling loads against heating loads, which ties into some of Robert's resiliency strategies, which were really important to him. If the power were to go out and for some reason he lost any mechanical cooling, we wanted to still make sure that the house was going to be as comfortable as possible, not at risk of overheating. All of the packages provided were triple pane low E with various coating strategies. Some packages were on the low solar gain side, while some were on the high solar gain side. And the difference in price was about $6,000 between the highest cost and lowest cost package, which is definitely enough of a motivator for a homeowner to really dig into this and consider the best solution. Next slide, please. So one of the things I was curious about while I was running these models was how much windows actually change the heating and cooling picture. Specifically, what happens if you go with a high solar gain window package that brings in free heat versus a low solar gain package that blocks out that heat. In a cold climate like ours, you think that high solar gain is always the winner. More sun, less furnace runtime, but the trade-off is that the same glass can make your house warmer in the summer, which pushes your cooling load up if you have air conditioning or a heat pump. On the flip side, the lower solar gain windows keep the house cooler, which is great from the resiliency standpoint, and especially during heat waves, or if your mechanical system fails. But they also block that free winter time solar heat, so your furnace ends up doing a little bit more work. And as you can see in this AI image where physics absolutely doesn't exist, this guy's just as confused as we were in trying to balance those trade-offs. So in the case of this project located in Crow's Nest Pass, where wintertime has longer days and clear skies, we chose a path kind of in the middle, which was a more balanced approach. Next slide. So when we did the comparison for the windows, the results through with the results through Volta, Volta Snap was our modeling software we used. We used a pre-retrofit model as a baseline, so before any renovations took place. Keep in mind with the various improvements in the envelope as well as air sealing, these results will differ. When we ran the various packages, I thought there would actually be more of a difference in total energy savings, but regardless of the windows chosen, installing triple pane windows did cut heat loss up to 11% in some cases, which was over half of what it was pre-retrofit. Looking at the comfort improvement, it was pretty much the same across the board as long as we went with triple pane windows. And the biggest impact was the cooling load reduction with the low solar gain windows, which was unsurprising but saved less energy overall, kind of reflecting what Mark had said previously. For the operating costs, every triple pane package saw reductions, but the range was small, was about $55 to $125 per year. So homeowners, if they're choosing windows, it shouldn't necessarily be in relation to lowering their annual energy bills. Rather, they should be choosing windows based on overheating risk, energy goals, overall energy goals, but not necessarily bill savings. Across the board, we only saw a modest reduction in solar PV requirements offset consumption. And the final choice ended up being a middle price package through Geldwin, which had one of the lower U value ranges and an average mid-level solar gain. So the final strategy wasn't a high versus a low solar gain approach. We maximized solar gains on the south side and blocked east and west gains in the summer to reduce overheating during the morning and evening times, which in Alberta, unless you live here, you don't realize how uncomfortable those spaces can get in the mornings and in the evenings. And so it was really important to make sure that those rooms were as comfortable as possible. Luckily, Robert had observed during the summer that the overhangs on the southwest or south side provided enough shading to prevent sunshine for directly impacting the comfort on those south-facing rooms, and were positioned to benefit the home for wintertime solar gains. Another factor that was considered was, as Robert mentioned, increasing the window sizes by, he says about 20% on the south. But then with his further analysis, he found actually that by increasing the gains instead, the results evened out. So in order to reduce the price of the windows overall for those specific windows and make it easier for him to install, we just upped the gains and the results were the same. So to answer the question about low gains versus high gains, it depends. In other climates, the approach may not have been the same, and a different strategy may have been used, but in this case, it works. If you want to hit the next slide, please.
One thing I'll chime in real quick is part of the reason why we did skew slightly towards more solar gains rather than less was the thinking that with the future solar array, when we do need to use the energy for cooling, happens to coincide with when it is most abundant. And so that helped to justify leaning a little bit more to a higher rather than minimal solar gains. If we were in a climate where their winters are typically overcast, that probably we would have chosen that differently.
Yeah, great point. Yeah, so the point here is you never have to choose a good window versus a bad window unless it's a really bad window. But you want to choose the problem you want to solve. It could be reducing heating or cooling loads. It could be solar protection or comfort or energy savings or a combination of these. The right answer depends on your house, your exposure, how you live in it. And we chose the balanced approach. I think we'll probably use this approach similarly in other projects across Alberta, just based on our climate. You can see here, this is some just the results for the windows chosen, pre-retrofit only. So you can see that there was improvements in, the heating loads. The percentage improvement for the windows specifically was substantial. So an 8% difference, 11% difference on that end. I'll give it back to Robert.
One other thing that is worth mentioning, the frost issues that you saw on the picture a few slides back, that was with the existing windows, which were aluminum frame, double pane, and that was at about a minus 25 temperature. Some places in Alberta are regularly colder. Um, in contrast, the new triple insulated windows, I have not only not had frost, I have not had even condensation, which has been amazing. The one exception was one day it was about minus 25 outside, and we decided to paint and consequently disconnected the thermostat from the wall, which disabled the HRV and heating system. Proceeded to paint for 6 hours. And around that time, I noticed that there was a little condensation beating up on some windows and realized that that was because we had had no HRV function and no heat. Amazingly, due to solar gain and the improved envelope of the house, we'd only had a temperature drift of about 2.5 degrees in 6 hours at a 40 degrees Celsius delta, and turning the heating system on for about half an hour and the HRV on boost for 2 hours made all of the condensation disappear because we had gotten up to a relative humidity of around 65%. And in 2 hours, it was back down to 45. So I was very impressed with how quick we bounced back and how well the solar gain as well as improved efficiency of the house proved in a situation that was effectively without power on a very cold day. Some of the things that we found in this project, there are increased costs being further away from a supply source. There's fewer trays to choose from, and you have to perhaps be choosier because in rural areas, the attitude of we've always done things this way tends to be more prevalent. And so there may be a little bit of contractor education to be done in order to ensure that the build is made as good as it can be. This was a budget build. We were very much trying to see how well we could improve performance, basically trying to get all the low-hanging fruit, do the 20% that would get us 80% of the gains sort of philosophy for the choices we made, and improving the windows met that criteria. And then, of course, we were living through the renovation. That does drag out the process because you can't work as fast, you can't make as big of a mess, there's more cleanup. Sometimes work has to be scheduled around, lived-in activities. But by far, the project was a success. Due to the house previously had some minor mold and mildew issues. The renovation dealt with those, but thanks to not having issues with water ingress and condensation anymore, I've noticed that my allergies are much happier. The triple pane windows do wonders for silence. I can see the Crow's Nest Highway from my house looking out the window. I don't hear the traffic, which is amazing because it was rather noticeable before. And then again, Aero Barrier really saved the day. And just because it was an existing renovation, we did not completely gut the house. The main floor of the lived-in area received exterior insulation. So that meant that there was a million tiny crevices that need to be dealt with to create a well-sealed envelope. Aero Barrier made that possible in a way that days with a caulking gun would not have. So I was satisfied with that position, and it played really well with having to upgrade the envelope around the windows as well, how we tied that all in together. There's a quick construction detail just showing we did something a bit unconventional as a way to we used a flanged window. As Chelsah mentioned, we used the Geldwin JWC 8500 window, and it was a flanged window, which I went with for ease of installation because most people in the construction industry are very familiar with installing flanged windows and seemingly less familiar with installing a boxed window, which tends to be more common in a really high-end window. I wanted to go with something that anyone who has competent construction skills could install appropriately with the right instructions. I wanted it to be something that they're familiar with working with. And again, some more frosty window shots. It it looked that way quite often during our first winter here. There's just a quick recap. Obviously, as part of the net zero thing, we upgraded our mechanicals, but we were able to shrink the mechanicals significantly because of an improved envelope, and the windows played an important role in making that possible. And I think that brings us to our next construction team.
Absolutely. That's a great project, and really want to emphasize that relationship that gets built between the renovator and the net zero energy advisor in navigating this, because it's not just for net zero homes. It's for homes that you want to live in, full stop. So we're going to turn over to another net zero project. This is with Trent Doherty and Dan Cogan. So I'll turn it over to you, Trent.
Hello, my name is Trent. I'm with Level Up My Home, and this project that we had was for the Hennessy's. They had owned the homes since probably the late 90s. It was built earlier, but they had lived there, raised their family, then moved into town and decided to rent the house, and then are now approaching retirement, and so wanted to move back into their previous home, to a smaller home, and looking to do a major renovation. So some of the things we were looking at was open concept and just making the home more energy efficient with that.
There we go. Should be yours now.
Yeah, just whoa. Okay, try to back up here. Okay, so our home is located in Russell, Ontario, so just a small community outside of Ottawa. As I mentioned, it was built in 1998, and we did our renovation. We finished it in 2024. It's a small bungalow, so around 1,100 square feet. And I worked with Dan Cogan from HomeSol on the project. And for us, having worked on net zero home projects in the past, we wanted to take what we learned from that and apply it to a renovation. And this was our first net zero renovation. So it was a perfect project because we were doing a number of aspects of the home that need to be updated, and yeah. Sorry, I'm just having a little trouble changing pages. So this was a before and after. So this was in the bottom left was the front of the home. Before, there was a large hedge on two sides of the property. It's on a corner lot, so previously the hedge was probably a lot smaller when they planted it, and just became grotesquely big, and so we took all that out and we renovated both the interior and the exterior. The roof had been done just a few years before, so that was something that we were keeping. This is the backyard. Again, bottom left is the before, and then after. We did add a garage to the side of the home and a deck and a pool, and redid the yard and replaced the hedge with a fence on the street side of the property. This is the interior from the front door. So that, again, the bottom left is before. So the stairs were central in the home, and it was really divided up in the main area. You can see the kitchen there through a doorway. And so we moved the stairs to where the kitchen was, and then moved the kitchen to the opposite side of the home, and opened up the complete main area there. So kitchen, living dining room. And because we were gutting the home for the most part, we were able to relocate and change windows and such as well. So this is still in the main room. So from the back of the house looking towards the front door, again, you can see the walls are divided there. And then we have, I'm standing in the kitchen looking towards the front door. So we opened it up quite a bit. And then because this couple was approaching retirement, it was just going to be them. So the bottom picture shows basically the door to the master bedroom, but there was a wall there and a closet, and then there's another bedroom beyond. So we took 2 bedrooms and we made it one larger suite bedroom. And so there's a huge closet cabinetry. And then we added a cheater door to the bathroom, again, trying to keep costs down. So the priorities for the project, we wanted to have it be open concept, and make it like a lot of the new homes that are available now. So we relocated the central stairs, we updated all the finishes, and it was a priority for the customer to add a garage, which in itself was a challenge because we were on a corner lot and we had setbacks. So we did a tandem front to back garage instead of a side to side, which originally the customer had wanted, but the front to back is better than a single car garage. So the existing house being built in 1988 was not so bad as far as the original construction. It had blown in attic insulation, and so we were looking to top it up to R60. There were existing 2x6 walls with R20 bats, and we kept the R20 bats and we added R16 rigid on the outside. The foundation, we gutted the basement and re-insulated with R10 rigid and R22 bats. And we also added R10 on the floor, which did reduce the ceiling height a little bit, but added a lot to the comfort on the basement floor. Because it's a small house, that extra square footage made a big difference for them. They did have natural gas in the home, and we replaced it with a cold climate heat pump. We did keep the gas as a backup because they wanted a fireplace for them. They wanted the enjoyment. They loved the gas fireplace, and so we couldn't convince them to get rid of the gas. We installed a new ERV. There was no provision previously for fresh air. So we added an ERV, and we replaced all the windows with new triple pane windows. And we used a heat pump water heater. And at the end, we achieved an ACH of 1.58, which was pretty cool. So challenges in a renovation, trying to get the home to be airtight, especially in areas where there was limited access. As mentioned, we were keeping the roof on, so there were some just areas that were difficult to reach. Also, we did a lot of this project during the winter, so we kept the original insulation in the attic, and we're constantly chasing patches to keep holes in the ceiling, especially after the electrician went through to keep the heat in during the winter. And then some of the challenges were, as there'll be some pictures later, detailing around the windows where there were different finishes butting into the window, so it wasn't the same finish all the way around the window. We changed finishes, so that was a little bit challenging to try to manage that. Again, we're trying to keep the existing attic insulation more for us, just to be able to work in a warmer home and keep the heat on. The project involved interior and exterior work, and we focused on the air sealing primarily from the exterior, and we also added rigid insulation. And we resized a number of the windows and did relocate some as well we increased one of the basement windows in size to make it an exit window. And so as mentioned, Dan Cogan, over to you.
Yeah, thanks, Trent. As Trent mentioned, I'm Dan Cogan. I'm the net zero energy advisor that was on this project. And this one was close to home to me because I'm actually from Russell, or I went to school in Russell when I was a kid, so it was cool to go back there. But yeah, so this slide summarizes the real performance outcomes of the project and what those numbers actually mean for the homeowner. Starting with the energy performance, the home's annual energy use was reduced from 84 gigajoules to 44, which represents a 48% reduction overall. The air tightness improved significantly as well, from 3.2 to 1.58 ACH. And that's more than a 50% reduction, going from a 0.21 NLR or CFM per square foot to 0.08. So that was great. From a load perspective, the design heat loss dropped from roughly 26,000 BTUs to 14,000, which is a significant improvement and has direct implications on the sizing of the heat pumps. And keep in mind, this house isn't very big to begin with, so the loads weren't huge also to begin with, but still that improvement was impressive. We also saw a modest reduction in the design heat gain, and the upgraded windows came in at U1.0 with a solar heat gain of 0.39. So after everything you've heard today, you may see that this 0.39 and solar heat gain coefficient and think that it's too high, but the window to wall ratio of this house fell between 12 and 13%. And going back to what Mark said, when the window to wall ratio reaches 17% or higher, that's when you probably would want to explore lower solar heat gain windows. So anyways, these windows were chosen because Trent has used them in the past, and working with familiar product while still being high performance, keeps things simple. And as far as Trent has told me, they're more affordable too. So I think this kind of highlights that you don't need to overcomplicate things to build a net zero home, and the smart trade-offs go a long way. Overall, not to say that the windows, the high solar heat gain makes the windows bad. They're still great windows, but just wanted to mention that. Overall, this resulted in a 83% reduction in greenhouse gas emissions, even without the on-site renewable energy. So what does this mean for the homeowners? Well, first of all, it's lower energy bills. Nearly 15% reduction in annual energy use translates directly into lower heating and cooling costs. Second, improved year-round comfort. Reduced heat loss and better air tightness means fewer drafts, more stable indoor temperatures, better winter comfort overall. Because the loads are lower, a home can use smaller right-sized HVAC systems, and which improves the efficiency and often reduces the upfront costs as well. And the improved air tightness and better windows also make the home quieter and healthier, and with less odor, noise, dust, and uncontrolled air leakage. And finally, the home is future ready. These reductions in energy use and emissions position it well for electrification, renewables, and long-term resale value. So yeah, this project is a good example of how performance-based modeling and targeted upgrades can translate into the measurable and real-world benefits. Back to you, Trent.
All right. Here's just some shots of the exterior. We used an EIFS stucco, so we used a trowel-on finish on the outside. So I like addressing the air barrier on the outside. So much fewer penetrations. So it's a shot of that in progress. then just an example in the center picture of the different finishes, how they intersect with the window. It's just, you have to take your time and think about how water's gonna move, as Darrell mentioned, and every house seems to have its different challenges. So appreciate Darrell's insight on this as well, and you never stop learning. And then just another progress shot of the stucco, again, because we were putting the stone at the bottom. We had different thicknesses to work with, so not just from a performance perspective, but because the insulation on the bottom is a denser material than the one at the top, so we wanted the same amount of R value, but I wanted to gain, I ended up gaining an inch of thickness so that my stone wouldn't stick out too far beyond and just make it more difficult to detail. So just lots of things to consider that really nobody sees when it's done, but it's important to pay attention to as you go. And that's it. Thank you so much.
Well, and it's all those details that are hidden behind the walls, hidden behind, you know, the facing that matter, because as we see from, as renovators, when you take those windows out, you get to see all the stuff that goes unseen. So it's that attention to detail behind. One of the things that stood out from this project is it is also that integrity of the window is part of the envelope design, but to be able to maximize existing square footage. So a lot of folks come into this thinking they have to build additions or build on extra square footage because they are not getting optimal use of their home, the existing square footage, but being able to upgrade the envelope with the window selection. That was something, Trent, that I think you had mentioned, that you know, being able to maximize and like you mentioned, being able to use the basement area because of all of those decisions. So being able to leverage to the max before you start taking on considerations for additions.
Absolutely. Yeah.
That's good. So we've got hopefully everybody's grabbing out their phones, taking the survey. We really want to hear your feedback. All of our initiatives, this initiative is coming to an end at the end of March 31st, but there are always initiatives that we are looking at in promoting this work, in getting not only the theory, but also the practical projects out there. So before we get into Q&A, just please make sure that you fill out this survey. So we've got just about 20 minutes left, and we're going to dive into some of the questions that have come out. So Toby, I'm going to turn it over to you. You've got the pulse on a lot of these photos. I'm going to stop sharing so that our teams can have a little bit more view time when they answer the questions. I'll take it away, Toby.
Great. Thank you very much, Lynn. Yes, we do have lots of questions. I think this time I'm going to start with the most recent things we've been talking about. So we have a couple questions for the renovators. One that's come up a few times here, if you're willing to share the cost of your projects. People want to know, how much did the projects cost? So I guess Robert and Trent, if you're willing and able to share that, or if not, let us know.
In the case of my project, that the bill ended up just a bit north of 200,000, but that was in part due to the fact that we added an extra bathroom in the basement and made future provisions for an accessory suite, as well as properly building in a backup power system if the power did go out, so generator provisions, etc. So the cost may have been a bit inflated because we attempted to achieve so many different things with this project.
Okay.
And that's important context, because the incremental part for the net zero, and Trent, you'll be able to speak for this, when you're doing the work anyway for other reasons, there's decisions that bring it to net zero, but they don't necessarily carry the whole cost of the project.
Oh, for sure. If you're doing insulation anyway, bats on the wall. If you're installing an R20 or an R24 bat, it's the same cost for the labor. It's just the incremental cost of the materials. For our project, I don't really have a final number because we did the whole property. So landscaping, garage, fence, pool, everything. So yeah, I don't know that that would really help here, but we did try to manage costs along the way, which did make it feasible for the customer to add the pool this year rather than waiting for a few more years to add that. So keeping the house small, like you'd said, Lynn, not adding additions to get that space and just reusing the space in a smart way helped the budget a lot.
One of the asks from Enercan on this project was to find cost-effective approaches to deep energy retrofits and net zero. And one of the absolute top, approaches is when you're undertaking a major renovation, engage with a net zero EA, see what the opportunities are, because that is the time. It's similar to when you're just doing a kitchen reno. Take off that drywall, see what's happening behind those cabinets and around the windows. That is the most cost-effective time to get in there and see what is unseen and what may be causing structural damage, as well as health and indoor environmental quality implications. All right, let's go on to the next one. Thank you.
There's a question for the renovators, and potentially maybe for Darrell, about pocket style windows, which I'm not familiar with. The person, Gil, is asking if that she thinks they're Energy Star eligible, and what are your thoughts, opinions of high performance retrofits with this type of window install? Can anybody comment on those? Are they easy to install, harder? Do they work in high performance applications?
Well, I think I'll just jump in quickly. I've never used them, but I've seen them quite a bit. They are basically just a regular window, but they're designed to fit into an opening that's been prepped and ready. So they call them a pocket window. They're very typical for the old wood. What do you call those? The windows that slide up and down, like the upper
The
lower,
double hung or
the
single hung
double hung
sliders?
window. There we go. Thank you for clicking my brain. So with the double hung, like if you just pull all of the materials out of the middle of the window, you can leave the casing and the frame and everything. And in all those old windows,
So you keep
a
that
lot of
old
times everything was
style.
fur, so they're very protected. So you will get the exact same window. It's just easier to install because basically you just slip it in. It's basically the guts of your window are being replaced is all it is. So
Yeah, I think now that you've enlightened me to that, there can be in that case you end up with more frame and less glass, which can be a concern, especially if it's a smaller window, but on larger window.
yeah,
probably
so you'd
work.
have to calculate. You have to do a manual calculation for your energy, and, because you're not going to do it in the traditional method.
Right.
And I would imagine
I
one of
would
the
add,
concerns. Oh, go ahead.
the thing I would add to that is I've used that on one previous energy retrofit, and it cut way down on my labor costs. However, that does deprive you of the opportunity to ensure that that you don't have any issues with the rough opening, because now you are prepping the existing box that is inside the box, so to speak. So I used that for all of the windows except one where there was evidence of some rot at the edge of the existing window, in which case I still had to rip out the entire thing and do it the normal way. And I went back to my supplier and ordered the slightly larger window to fit in the now slightly bigger hole. So it is a great cost saver. It can make the renovation more affordable because it goes faster, but you do run the risk that as you take the window apart to put in the insert, you may find that there's additional damage, and that may cause some scheduling issues.
That was exactly the point I was going to make about the lost opportunity to inspect where we know this to be a pain point when we go into existing houses. That's exactly it. All right, Toby.
So a couple questions for the energy advisors. One is, have you considered, I think this one's more for Chelsah because you talked more about the solar heat gain and the different orientations. Have you considered a mixture of high and low or moderate solar heat gain options depending on the orientation of the windows? So low, maybe lower gain on southwest facing and higher or moderate on north and east where there's
Yeah.
less direct sunlight.
Well, that's exactly what our approach was the higher gains on the south, lower gains on the east-west, rather than high across the board or low across the board. And it works well in Alberta with our, as I mentioned, the longer days, a ton of sunshine. And for this particular project, with the way that the overhangs were originally designed, now in a new construction project, you can, you have high gains across the board as long as your overhangs are designed appropriately for that house. I guess we could have added higher gains and then Robert could have just whipped up some additional sun protection on the west side easily enough. But in order to reduce the complications on the construction side, just the glazing choice is a super easy strategy to achieve the results we were looking for.
Great.
Can I jump in on? I just wanted to say it was really excellent to see the attention to solar gain that was paid on both these projects. And additionally, as Chelsah was just mentioning, something that we didn't talk about in great detail is external shading as a strategy. And that can be both on the house, but also on the site, which starts to stretch beyond the limits of what we represent in an energy model. But, hedges, trees, deciduous versus evergreen trees, and seeing the attention to detail that went into the window selection from a gain perspective and all the, Robert having lived in the house, understanding how the overhangs were performing on certain orientations and that playing into the decision-making matrix is exactly what I think that question points to, the opportunity to be even more refined in your detailing of choice than just picking one number and sticking with it. Very cool.
And also that dialogue of understanding the when. So when do we want to take advantage of that solar heat gain? Because overheating is becoming more and more of a concern. There are many areas that did not require forms of air conditioning that are now moving into that concern. And so that conversation and the navigation of that is really critical to bring in those experts. I think we've got room for maybe two more questions.
Two more? Okay. Question for Darrell. Are windows about where to place the window in the within the opening? Are windows always installed exterior of the sheathing? I've heard some talk that it's more efficient to recess the windows closer to the interior, but that creates its own detailing challenges. Comment on that, Darrell?
Yeah, I think that's what it comes down to is there's different products available. Like I know Geldwin and some of those other companies, all weather in the West, will offer a window that can sit in the middle of the rough opening. So it really comes down to the design of the window. But in any event, when you move the glass in closer to the interior, it's easier for the air and the circulation in the room to reach the surface. So you definitely get less condensation potential if you can get the glass in closer to the interior.
Right. But more exposed sill on the exterior to manage,
Yes.
I suppose.
Yes.
And I just want to add on to that because we did have one project where it was the fire separation that demanded that the plane of the window stay in the original plane, because when you add on insulation and if it's all non-combustible, what it was, the solution path to, I think there was it was either take all the windows out of that wall or all non-combustible and the window stays in the original plane where that is. So you may be having other factors that drive that position within that wall assembly.
Yeah, and I think the detailing complexity can really play into that balance with the functionality. I've seen projects with very thick walls that wanted to make use of the interior space.
Right.
And then you consider if you go with a high enough performance of window with a really low U value, your condensation risk comes down, that air washing effect is less important. You can get away with that sort of thing. But what I would emphasize is the most important thing for us to get right is the water management detailing. And so the placement that gives you the best advantage in that respect is often, I think, the one that you should look at first.
Yeah, and I'll just chime in and think about where you're going to block and support the glazing to transfer it through. So if you're used to using a window that the glazing on the exterior and you're moving to a window with the glazing midpoint, make sure that your framers understand where that blocking goes so that it's in line with the setting blocks in the frame itself and transfers that load.
And just one more follow-up directly related to that point by Mark. Darrell, how do you recommend flashing the sides of a window when there's no brick mold or flange?
When there's no brick mold or flange, well, if you're putting a window in and you're just using a regular window, a box window, and you're inserting it into the opening, then you're going to have to work with your exterior cladding contractors to figure out how you want to detail that. So there is a slight difference in how you detail those openings. If you're protecting the openings, you tend to protect the bottom of the opening with a flange window more, knowing that the flange protects the side and the top, versus a box window where you're probably going to put peel and stick around the entire rough opening. And then you might be adding brick mold yourself. You might be adding a detail or a trim or maybe a metal flashing around it. But either way, you follow the same principles. And so once the window's in, then you're thinking of the window and sealing it and detailing it the way you would typically do it. And then think of all of the other materials you put on the outboard of that as the same as your cladding, as first plane of protection. So whatever water gets behind there, pick up the water, take it back outside in those locations where you can have a flashing in the lower section of the window.
Okay. Thank you very much. Unfortunately, we didn't get to everyone's questions, but appreciate them very much. Back to you, Lynne.
All right. So I just wanted to thank everybody on this panel. We are, like I mentioned, this is the last of five that we had planned. And what a great way to end off this series. A lot of great information, a lot of great questions, really good projects. And so I just want to really thank our panelists today. I do want to mention also, we do emphasize how as there's a navigation of all components, the integrated design process. So when we look at windows being part of our airtightness solution, a part of our envelope solution, when you undertake any major renovation, we're always highlighting the radon aspect, because this is something that you don't get that visual where you can see the rot, the mold, or you can smell the mustiness. So this is something that the reason why it's the November plan starts in November is because it's really driven around the heating system. So when you've got your windows closed, when you're in that more enclosed heating environment. What I do want to emphasize is as we move into the spring, if you are undertaking projects that are major renovations, talk to your radon specialist. Find out a way that you can get some indicative information about what's going on in your house on this matter. So it's always a good time to start monitoring. There's better times, but it's always a good time. So what we include in our package is we do give links to various resources. There was the glossary that Toby, thank you for getting that able to share. We also have some information, I think it's mentioned here, from BC Housing that Darrell had referenced in terms of this topic. So as mentioned, we are now at the end of our 5 series. They are all available on the CHBA website. They're also all available on BKC's, on Building Knowledge video series Towards Net Zero Renos. So you've got ample opportunities to look at these webinars. We are also combining project video footage and testimonials on these different topics that we will combining in those as we move towards the end of this project and making sure that those are available. So as we close out today with all of the 5 different sessions, I want to thank Building Knowledge for all of the work. Kimberly behind the scenes who gets stuck behind the Building Knowledge logo, Mark and Toby, and obviously to our presenters today, thank you so much, and looking forward to what the next round of projects brings us. Thanks again.